Alright, this video is going to be awesome because we'll be talking about the three coordinate systems that you have to know for your Calculus 3 class. Of course, we are talking about 3D. We're talking about the rectangular coordinate system, the cylindrical coordinate system, and also the spherical coordinate system. But let's compare the rectangular and cylindrical first. For rectangular, first we start with the x, y, z axes. And let's say we have a point in a space somewhere here. We are going to talk about how to go from the origin to this point. First, we move in the x direction, let's say somewhere here. And then we have to move to the y direction, let's say somewhere here. And then we have to make sure that we can see the point above us or maybe sometimes below us. And then we have to just go up. So it's just like that. So we have the x direction, which is parallel, so that's also x, and then this right here is the y, and then vertically we have z, so we have x, y, z. Done. Now, what is the cylindrical coordinate though? Here we still start with pretty much the same picture, x, y, z. And let's say we still have a point in the space. But instead of going left, right, forward, backwards to get to this point, in the xy plane, we are going to do the polar way for the two-dimensional case. Starting by looking at the x direction, and we have to rotate. We are going to rotate so much so that we can see that the point is like right over there. And then we have to move so that we can be under the point. And that distance that we go out, we call the r. So we have r theta just like the good old polar coordinate for the two-dimensional situation. Once we can see the point above us or below us, we go up or down in the z direction. So that's z. So this right here will be r theta. Again, just like the good old way, we put down r first and then theta, and then the last component is z. Cool. Now, how can we go from rectangular to cylindrical and also go backwards? So here, suppose we have x, y, z given. How do we get here though? Firstly, let's talk about why this is called the cylindrical. I forgot to mention that. It's cylindrical is because the way that we move in the xy plane is like circle, right? Circular. So we really just have like circle like this. And then once we get to here, it's also circular. So it's like a cylinder. Yeah. Anyway though, x, y, z, how can we get to r theta z? First, we have to talk about the angle from here to here. That is angle theta. We have the opposite and also the adjacent. So that's just tangent. Tangent theta equals y over x. And then let's talk about the r from here to here. Well, that's just Pythagorean because this right here is the right triangle. So r squared equals x squared plus y squared. It's the same conversion for the 2D case as well. Lastly, z and z are the same. So z equals z. Done deal. Now, how do we go backwards? Given r, theta, and z. Z is the same, so we don't have to worry about that. But given theta and r, well, we have to talk about how to get to the x direction. So let's say this is how far we have to move. Yeah, so that's x. So by looking at this right here, we have x, and then this right here is the hypotenuse, and then we have the angle. So we can use cosine. Cosine theta equals x over hypotenuse r, and then multiplying r on both sides, x equals r cosine theta. And then for the y direction, well, it's just going to be the opposite, which is sine. And then we have y over r, and then multiplying r on both sides, y equals r times sine theta. And lastly, z is just equal to z. So as you can see, this right here is not so bad because these four equations are what we saw in the 2D case as well. Now let's talk about rectangular versus spherical. And I think this is the hardest case, so pay close attention to this one. For rectangular, it's just like what we did earlier, so let me just put down the same picture again. We have x, y, z. And let's say we have a point in the space. So we need to know the x direction, the y direction, and then the vertical direction, like so. So x, y, z, and that's how we label this point. Now, for spherical, pretty much the same thing. X, y, z, like so, and then we have a point in the space. But how does this work though? Let me do a demonstration. Let's say this point is just like a fly in my room somewhere over there in the space. And what I have is a laser gun. And I'm going to hold a laser gun like this, right, vertically upward. And I'm facing this direction. What I need to do first is I will have to rotate it like this. So that's the first rotation. And then because the fly is not up there, it's somewhere over there. So I will have to rotate this, right? That's the second rotation. Rotate my arm like that. And once I can aim the fly, I'll just shoot from the origin to there so I can get rid of the fly. So first rotation in the XY plane, we call that theta, just like what we did earlier with the polar case, also the cylindrical case as well. And then I will also have to remember from here, the positive z-axis, this rotation. So the second rotation is 180 degrees, right? We call this rotation phi. And then we are going to go from the origin directly to the point. We call that distance rho. So this is not p, it's rho. It's just the distance from here to here. We write this point as rho, theta, and then phi. Ooh. Okay, now you know the deal. How can we go from this to that and that to that? Here, start with rectangular to polar. Firstly though, let's talk about how we can get from the origin to this point. In another word, the rho. Here, it's just a distance formula in the three-dimensional case. So we can say rho squared equals x squared plus y squared plus z squared. The 3D version of the Pythagorean theorem. Very nice, huh? Next, we will have to talk about the angle theta. That's this rotation, right, in the xy plane. So we can just do what we did earlier, opposite and adjacent, so we can use tangent, and that's just y over x. Now, the last one is the trickiest one. How about the angle v? This right here is the angle v. How do we take care of this? The trick is we have to look at this triangle. In fact, this angle is a right angle because we have the xy plane and then we have to go from here upward, so it must be a right angle. So if you look at this triangle, here we have the z-axis. Let me put this down right here for you guys. Here is the z. And then we have this, which is rho. And then this angle is what we call the v, right? Now, here's the deal. We are just going to draw a line straight down. I'll put this down in blue. This is exactly the z, right? So we have z. And then of course this and that are parallel. And because this is v, this angle must also be v because they are the alternate angles of the parallel, right? Parallel sides. So what can we do? We have adjacent and then hypotenuse. So we can use cosine. Check this out. We can say cosine phi equals adjacent, which is z, over rho. But I don't want to put on rho because we're given what? X, Y, Z. But it's okay because we know rho squared is equal to this. Just take the square roots on both sides. So we have square root and just do a positive version. X squared plus Y squared plus Z squared. So that will take care of it. And then I'm going to leave this to you guys. Of course, you can also use inverse tangent and inverse cosine to solve for theta and phi, but you have to do it carefully. The best thing is draw pictures, but sometimes it gets extremely tricky, so be careful. Alright, so these three formulas are what we need to go from rectangular to spherical. Now, how can we go from spherical to rectangular? Yeah, this is hard. First, we are given rho, theta, and v. Let's talk about how we can get to x, which is this distance here. Right, that's x. Let me actually just complete the picture. So this is x, and then let's say here is the y, and here's of course the x as well, and then let's say this right here is the z. To get x, it looks like we should complete this right here, right? So let's go ahead and just draw it right here. And of course, that will be r in the polar way, right? So if you look at, I cannot use this picture. I will have to do what? Firstly, we have theta given. For x, we can say x is equal to r times cosine theta. That's okay. And of course, we can do the same thing for y. Y equals r times sine theta. All right. But the thing is, how do I find r in terms of rho, theta, or phi? We can use this picture. Check this out. Right here, per our discussion earlier, this triangle is right here. So the base right here is precisely the r. So if you don't want to look at z, just look at phi, which is given, rho, which is given. We can figure out r by using sine. We can say sine phi equals opposite over hypotenuse. Multiply rho on both sides, r equals rho times sine v. Now we can just put this right there and right there. Haha. So ladies and gentlemen, this right here gives us, we have rho sine phi and likewise rho sine phi for both of them. But here we have to multiply by cosine theta and then sine theta for the x and y component. Cool. Now, lastly, how about the z? Here we have the z earlier, I just erased it. Z. For z, all we have to do is, because we have the rho already, we can just do what? Cosine, right? We know z, I'll just put this on real quick. Cosine v equals z over rho, just like what we did over there, and just multiply rho on both sides. So z is equal to rho times cosine v. So ladies and gentlemen, these 6 are the ingredients that we have to go from rectangular to spherical, spherical to rectangular. Here's the last one, cylindrical to spherical. So for cylindrical, here we have x and then y and then z and a point in the space. What we'll do is, on the xy plane, we do the regular polar way, right? So we need a rotation theta, and then we need the r, and then for cylindrical, we just need to go from here upward. So here we have the z. So r theta z. Yeah, so let me just make this dashed line like that. And again, it's just a bunch of circles. Yeah. Now for spherical, so again, x, y, z, and a point in the space. Like this, right? Fly over there. I will have to rotate my body, and the second thing is I have to rotate my arm. So this is how I rotate my body, and then this is how I rotate my arm, and then I will go up from here to here. So the first thing is rho, the distance from the origin to this point, and then the second thing is the first rotation of my body, and then the second rotation, v. Now you know the deal. How can we go from here to here? And then go backwards too. Alright, so check this out. First, I have r theta z. How can we get rho, which is the distance from here to here? Well, if you look at this right here, we have a nice triangle, right? So I will just put this down on the side real quick. We have rho, and then this right here is z, and then the base here is r. It's a right triangle. So of course use the Pythagorean theorem. rho squared equals r squared plus z squared. And in fact, this is the reason why Pythagorean theorem also works in the 3D situation, because r squared equals x squared plus y squared. Alright, so that's that. And guess what? The next one is theta. It's the same exact theta. So theta equals theta. Yay. Finally, how can we get to v? V is this angle here. And per our discussion earlier, it's the same thing here, isn't it? Yeah. So remember, we are given r and z. So we are trying to figure out what v is. How can we do it? For this right here, we can just use opposite over adjacent. So now if you look at this picture, yes, we can use the following. We can say opposite over adjacent. So we can say tangent v equals r over z, and then just work with it. But once you use inverse tangent on both sides, because the range of inverse tangent goes from negative pi over 2 to pi over 2, for the angle v, we want it to start up here and then go down 180 degrees, right? In other words, from 0 to pi in terms of radians. So it would be better if we look at this and use cosine, because the range of inverse cosine is from 0 to pi. It's exactly what we would like for the angle v. So let's look at this picture, and the rho right here, we can look at this as the square root of r squared plus z squared. So if we set this out with cosine, we can say cosine v equals z over rho, so z over square root of r squared plus z squared. And then once you take the inverse cosine, well, the range of inverse cosine is from 0 to pi. That will give you the v much better. So that's that. Alright, finally, if we have spherical, how do we get to cylindrical? Here we go. If we are given rho, how can we get to r? Let's take a look right here at this picture, right? We have rho, we just have to drop the perpendicular line down, and then here is the r. And of course, this is also z. So we have this triangle. So I'll draw this one again. So this right here is rho. This is v, but this right here is also v. And here is the r, like so. So let's just look at this picture first. To get r, we can do opposite over hypotenuse. So sine v equals r over rho. Multiply rho on both sides, we can say r equals rho times sine v. And the next theta, it's the same theta. So this is so nice. Theta is equal to theta. And lastly, ladies and gentlemen, we have to get z. How do we do it? Adjacent hypotenuse. So we can say adjacent over hypotenuse. So we can say cosine v equals z over rho. And then multiply rho on both sides. Z equals rho times cosine v. Done.